guys, welcome to another PlayBASIC live video. It's about the third or fourth time I've shot this thing. Getting pretty tired of the whole crashy computer thing. What we're going to do today is we're going to convert a bump mapping demo written in Dbpro, and for some reason I've optimized this for someone else, and I just found the source code in my big bucket full of source code sitting on my other hard drive, and thought it might make an interesting example to port it. So let's get to it. Let's do it. I've done this a few times, so here we go. We'll go through line by line pretty much. So set display mode is the screen mode. So this would be open screen in PB, and we would need an extra flag there, don't we? So we'll have one for windowed mode. Set window title, you be title screen in PB. All good so far. Vector should be the same. Vector 4 should be the same. There's a bit of a collision there. We'll see if that compiles. As Boolean, we don't have a Boolean type. So we'll just go with an integer. Let's hit compile. What we'll do is, as we move through, pretty much, we'll hit compile a lot. All right. So what's it saying? We've got global in front of a dim. We can't really have that in PB, so we can get rid of those. As integer, we don't need that. It's redundant. Global dim. Global dim. Someone down the bottom there. What was that? Global screen, whatever that is. So I wrote this yesterday, or the day before, and the capture failed, and the audio was wrong, and it wasn't having a good day with it. That's not, it's a bit of a bummer. Okay, those dim statements look alright, but we've got an obvious problem here. Screen width, what is that? In PV, it just gets screen width, so we'll do that. Use replace for that one. Bit lazy, hey? Hope you're all doing well with your forced lockdowns of all different types and descriptions around the world. We're pretty much over it here in Australia, but in many ways we're over it. We've kind of escaped, I wouldn't say unharmed, but certainly not as bad as some other countries. So I hope you're doing all right. All right, so screen height is another one there. We use the get prefix in our commands. To read properties, we pretty much have the get prefix or the get keyword. Hit replace. Replace all, thanks. Yep, all of them. Looked alright. Let's go back to the top where we were. Might do a quick save with that actually, so we don't lose what we've got. Hit compile again, see what we're up to. Screen is screen type. Global. Okay. We'll just dimension these structures here. These are a couple of vectors. Alpha is integer. We don't really need to do that, but for consistency we'll leave that there. Dim constant. Now that's a keyword in PV. We can't really have that. So I'll call it const. And global time. Just dim time is that structure. How far have we got? Hey, we've got past that. Pretty cool. So all our declarations they're compiling, but whether they're working or not, that's a different conversation altogether. Sync on, they're not really needed. Hide mouse is not really needed. Oh, it's missed one of those statements. So get screen width. So we're reading from the system what the screen width and height is and storing it in a structure for later on, for referencing later on. We probably should have done that up here somewhere, really. It's been I remember seeing this. I remember this program, but not necessarily why it was written. I have no idea why I was sort of messing around with it. Anyway, so calculating a size in pixels or in bytes actually. So the screen width by the screen height times 4. So each byte, sorry, each color in an image is going to be 4 bytes. So here, so we need mem blocks to represent those images. Now in PB we could do this with actual images, but we use banks just to try and mirror this code as much as possible. Create bank and another create bank. Thank you. Hope the audio is working better this time. Yesterday's session recorded the whole thing. Was kind of happy about it. And then went back as I was saving the last section. The whole thing crashed, and that was the end of that. Copy the source buffer. Get memblock pointer. So this is get bank pointer in PB. They're effectively the same thing, really. They're doing the same job. We're just allocating a bank of memory or a chunk of memory, and then we're referring to that by its handle or an index in this case. So we can get a pointer, the actual location in memory where this bank of memory was allocated for us. For bank 2, for bank 3. Let's give it a go. See how much further we get. We get to here. Okay. So in Dbpro, you can do an implicit pointer. So you can do sort of a dereference here and read when it's on this side of the expression, we're doing a poke to memory. And when it's on the other side of the main assignment, it would be a peak. Bit of a basic trivia there. So we can just replace this with, I could rearrange this and write this with integer pointers, but I won't in this case, because that would mean fiddling around with these additions here as well. So I've got we're reading that pixel there. Sorry, we need to do a poke int, not a peak int. And that's just shorthand for poke integer. Probably should be poke integer as in a longhand there. Poke int, thank you. I'm not actually sure how this is working, this program. But mapping is just a way of you create a normal map and a light source, and you get kind of specular highlights and shadows on top of a surface. You would have seen it used in modern games. Looks okay. So we've got a poke into memory, quick compile. How far have we got? Ooh. When I first looked at this expression, I was going, ooh, what's wrong with this function? It's a function here that's a user defined. We might do a bit of fiddling around with this function itself later on. But for now, we should just be able to call that function. It's just telling us, PB is just telling us there's a syntax error, and what it means, we're going 1,000 integer divided by 30 integer. So we get an integer result because the two numbers on either side of the division are ints. So this int here is superfluous. We don't need this. Chuck it away. Well, let's just see if we get past it. We do, so we won't worry about anything else. Get mem block pointer, so we get bank pointer. There's one below that as well, bank pointer, thanks. And another one down there. Bank pointer. Yeah, so we're computing where things are, and these these buffers. Just tab that out a little bit so it's kind of easier to see what's going on there. Got a clip at the end, looks alright there. Another quick compile, cheeky compile we'll call it. Okay, so we're reading a pixel here, so we use the peak. That asterisk in front of it means a peak. We're using this integer as an address in memory, and we want to read the memory at that particular address and store it back in this variable here. So I'll do the same thing over here. Peak int. Any more of those? There's one there. And one there. Not quite sure what that's doing, but we'll have a bit of a look at that later, I guess. There's a few things there that look a bit dodgy. It's got a mask that's wrong. Same as one there. That code's splitting up a pixel and multiplying it by a level pretty much, then dumping it back into memory. So we'll do a poke int there. The same process. Let's see if we missed something in that bit of code. We did. Those ands, we don't need those. This does the same operation. So we're masking off those pixels there. When it moves this down, it should have a mask there as well, just in case there was something in the alpha channel. But I guess that we're assuming the source images we're working with have already masked off. And we didn't put our poke into that one there, so good catch, I think. Some of the logic here we could probably use, max val or something like that, or even pack up some of this in other ways. But I think what I've done when I've optimized this code originally, I've unrolled some of these inner loops to get rid of the loop overhead. Dbpro says, even though it's compiled to machine code language, it has very high loop overhead for 4 next loops. A bit of a cheeky save, hit F5 again, see how we go. What do we got? Oh, got a peak we missed there, of course. Any more? Yep, another one there. So you notice I'm not really paying attention to what the code is doing. I'm just assuming that the code's going to work the way it is. I don't actually think it will. You might have to tweak it up and do a bit of debugging. Oh, okay, we've got further. So we're out of this loop section here, which does, I think this does the actual effect itself. Well, it must be, because we're lighting the pixels and putting them in the buffer. That's pretty good. If this pixel here is 0, for example, if there's lots of zeros in your image, or your light map in particular, or it's calling this the environment map. We could save a bit of work there and only fall through this logic here if it's doing non-zero. But anyway, so we're locking the surface. In PB, that's lock buffer. Get mem pointer. Okay, sorry, bank pointer. That's where something is stored in there. We've got a back buffer pointer. Okay. So the back buffer in DB terms is the screen, pretty much. It's the address of the first top left-hand pixel of the screen. So for us, we'll make a variable here, screen pointer. Get image pointer. Now in PB, image 0 is the screen, and we also need the pitch. If we start dealing with the back buffer, we'll need the pitch, and it's represented over here actually. There, it's right there. So I'll get pitch get image pitch, and that should do the same thing with any luck. Now the pitch is just the number of bytes that represent one row. You might think that that would be just the screen width multiplied by the number of bytes per pixel, but it's actually not, because screen buffers or the screen itself is often aligned to a power of 2. Depends on your video card, how that's done, so that's just what you need to do, unfortunately. And even with surfaces like FX surfaces in PB, it will pad those to powers of 2. Although it does depend on what version you're using there. Well, for now, we'll just say that's a good guide to live by. All right, so we've got a destination address. So we're copying something to the screen. We've got a source row address, which is obviously what we're copying from there. That's all cool. Yeah. This is doing oh God, what is this doing? It's doing a memory copy pretty much from whatever's in this memory at this location here to the screen, copying it row by row. So when I did this yesterday, I did a memory copy here, so we'll do the same thing. Copy memory, source address is the source row address, and the destination is the destination row address. And the size is going to be, how many bytes do we need to copy? Screen width. Bytes per, no, it doesn't really matter. Yeah. So we just go screen width. There's an obvious optimization there, isn't there? What I mean is this has been calculated every single time it falls through this loop, even though these values here are constant. We don't really need them. This copy loop here should do the same task. So we're copying the row pixel by pixel, there's nothing after that, so we should be able to just comment that out. Actually, I did see one thing that's different. This inner loop here is unnecessary, but it's not just copying the memory, it's clearing it as it goes along. So we need to do something else. We need a fill memory in here. Fill memory, and we want to fill the source memory with zeros, because just poking zeros into these locations here, so we should just do the same thing. Source address. What's the syntax of the command? I've actually forgotten. Excuse me. You can have a pattern with fill memory too. I remember that. You can have a mask as well. So you have a write type. So you can rather than just overwrite what you're filling, you can AND it or it or exclusive or it. Which I've found handy for doing things like simple encryption or that kind of stuff. Right, so our parameters, what do we need? We've got this is the number of, okay, we've got a pattern, that's it's going to be a 0, and fill type is what? Alright, so we set that to 4 if we want the fill to render integers. That would be the last parameter. This is the fill value. That's the last parameter solved, and this value here will be, if we're filling integers, we want to just render screen width. So that's the number of pixels to clear, and they will be integers in size. Yeah, that makes sense. I hope that makes sense. So we've really replaced this unrolled chunk of code with 2 bits of built-in functions. So they'll operate very quickly. These two bits of code here will anyway. Unlock back buffers, that would be unlock buffer in PB. And a cheeky save and another test compile. What have we got wrong this time? Oh, we don't need that. Oh, escape keys. It's actually this. Display the frames per second, display the map time, whatever the map time is. Got some undims there, we don't need these. We're going to undim them. We actually don't need those at all. When the end instruction here is hit, PB's runtime cleans up all this stuff for you, so you don't really need any of that stuff. Here it's been tagged as GC, like a short for garbage collection. So we've got to the functions at the end of the program, and we still aren't working. Local, right, so length is going to be a float, so we do need the decoration, the hash at the end of it. And here, and that should make that work. We do have a distance function in PB, actually. We can replace this with, I don't think it's going to be of any benefit to us whatsoever. Get rid of that for a second. Oh, right. So it loads these two. It loads an image in and then the bump map of the image as well. And if I look, when I ported this the other day, or yesterday actually, these two loops are the same. It's doing the same thing. So we'll make a function out of that and we'll save it ourselves. We can't load this image format here. It makes no sense in PlayBASIC. But I've already converted the image to a PNG, so we can just load the PNG in its place. So I'll grab this bit of code. I'll put this above that label there, just so I can see it on screen actually. Function, we'll call it load image to array. We'll have a file name. We'll have, I'll call it image. That's a bit of image. And function, thank you very much. Let's hack it. Let's get this thing going. Right, load image. This is a temporary image pretty much, so we can just kind of throw this around a bit. Load image into slot 1. I have no idea what that parameter does, so we'll just assume, we'll just ignore it. Paste image. Okay, it's drawing. Alright, so they're loading an image in, drawing it to the screen, and then running through point by point and grabbing that. You don't need to do that in PB, that's rubbish. Get rid of that. Delete image. Lock buffer. So what we'll be doing is we'll unlock buffer. So we'll load the image in. We'll make that file, by the way. We're loading it into slot 1. It's a bit rough there, really. Render to image 1. Doesn't feel right, really. Get screen height. What are we doing that for? That's not. What if the screen and the image are loading at different sizes, and we try and read the pixels off that? We're going to end up with problems. In fact, even the array here, it probably should size those out there. I think because the program is written as a demo, nothing's really thought that there's not a lot of thought put into it. So that the arrays are sized up the front and the image is loaded. Yeah, you know what I'm saying. So I won't be too critical of it. Well, like all demos, I mean, we all just hack them together on the spur of the moment. If we're rendering to image 1, we can just use get surface width, thank you, and get its height from here. image width equals the minimum value between image width and get screen width. So we'll kind of clip it to the screen size. I hope that works. I don't think we need to do that. I think the image is already pre-sized to the size of the array. Maybe I'm just being paranoid by adding that bit of, just a little bit of cleanliness to the function, but right, so image width. And the rest of that can pretty much stay the way it is. It's not the quickest way of reading the pixels from that surface into that array, but oh, surface, oh, thanks, MBN. So here we're passing in a two-dimensional array, or an image that has no dimensions until we get to here. So it'll expect it to be two-dimensional. Grabbing the point, we're masking off the R, G and B and just keeping those. Let's try and compile that. Alright, that didn't die in the function, that's pretty cool. So load samples. So this block of code can be replaced with we're loading it to the surface array, and it's that file name there. Let's be brave and cut that out. I can see a little problem with that. Actually, just cut all of that out. Right, so the second time we're loading the other one to an array called bump. Just assume that's been declared up the front, and we'll won't worry about the mask is different, see that? So we'll have another field here, and this will be the mask that's passed in. And we need this up on this function as well. We'll just call it pixel mask or something. And here, pixel mask. Put a comment on the outside of that. Do we compile? That's weird. It's starting to push itself to the back. I think so I had the help open. It's decided it wants to be an idiot. Oh, syntax error. Doc product 2 minus 1. Oh, that array. Yeah. So it's got that constant keyword there. We changed that to an array earlier on. I don't know why it's using that. Int const. Okay. Quick save. Quick test. Wow. We got to a point where the thing ran. And it didn't find the file. So that's pretty cool. Now I renamed those files. I put them in assets. I put a version of them as a PNG. Details, thanks. PNG. So we should be able to replace wherever that was. Oh, the error's, it's not a bad error there too. Unable to load image, title, assets, default _ color DDS, unsupported format. Better than the old errors. So that's not, we don't want to load the same thing twice. We want to load it to different places. Load bump, and it was PNG. Let's see if this thing will work. Image 1 doesn't exist. Very good. Image 1 doesn't exist. Render to image. Oh, hang on. When we load this thing, we need to render to screen. So we're loading our image, we're directing all rendering to that image so I can read pixels from it. There's another way of doing it actually, but we won't get into that really. We could get a pointer to the image and copy the memory out directly, but yeah, we just keep it the way it is. So we're directing rendering to our image, we're locking this buffer, we're getting our surface width, height. We probably should read a null pixel here. When you change the render surface and you haven't drawn anything to that surface, there's a potential for that, for the internal surface caching not to actually pick up on it. It's a kind of a byproduct of point and trying to make point faster. Yeah, I know. We'll just call it null pixel or something. Null pixel will just read a point. This guarantees that that will be set up at least the first time. And then once it's set up, any further points should be okay. Yeah, give it a run. Well, it's running. Nothing's on screen, but it's running. I'll take that as a bit of a win. I might just have a break for a couple of minutes and we'll continue on with the rest of it. Okay, welcome back. Just got myself a nice warm coffee. Hope you've got one yourself. Let's kick on with this thing. So before this thing compiled, but it didn't work, and I wasn't that surprised by that. So let's try and get it to work, and we'll give it a run. We've got a blank screen. That's pretty cool. Love it. It probably means two things, doesn't it? Is it running the rendering at all? What do these functions do? Okay, how does it work? So we've got our main loop here. This is our main loop. Effectively, this is the main. Those people who like that. We've got a field in the structure. It's being updated with this function here about every X number of milliseconds. Whatever 1,000 divided by 30 is going to be. More interested in. Right, so I've got the screen structure here. What we might do is we might make sure that's allocated. Equals new screen type. PB, or legacy versions of PB support this kind of automatic allocation when you write to a structure. But as we move on, we're kind of getting, well, not getting rid of that, but just trying to move people in this direction here. Constant, okay. And time there is the same, so we'll go time equals new time type, was it? Just go a quick save. Why is that down there? That's silly. I would have thought up around the screen stuff here, we could have really done this. See all those screen function calls there, we could just go, yeah, you know, put them up there, but we won't go hacking and slashing the code right this millisecond. Load samples. Let's put a break at the end of that. Let's just see if it's loading the stuff into memory. I have no idea. Got to have a break. Let's check our variables. What's in these arrays? So I've got a bump map array that's empty, that's nice. A back buffer array which looks like it's equally as empty. Alright. Our screen, that at least that's initialized, that's correct. So that part's functioning. Our light vector, we have something in our light, that's good. And the time, that's not working at all. Oh, we haven't called that yet, have we? We put a break before the main loop, so it hasn't been called. It's weird that so a bump map is not initialized. It should have been loaded up front, surely. And these are the bump normals, so they'll be empty as well. If there's no bump map data, there's no image data in the bump map array, there won't be any normals. Yeah. Okay, let's have a look see for that one. What have we stuffed up in here? Oh, I think we have stuffed something up. So we found our images there. Image, yep. And pixel mask. Image height, image width. Get surface width, minimum value. Well, let's just try something crazy and we'll go to print the image width and image height out just to make sure that they are actually something that makes sense. May not be. Console. Yep, right sizes. Good. Unlock that. Render to screen. Loading the image, rendering to the image, locking the buffer, grabbing a point, grabbing the width and height. I'll put the break in here because I want to know, is this image being filled up with something? Let's check it out. So go back to hit stop actually, back to variables, the breakpoint sitting at the end of this load image function. So I can peer inside that function and have a look at what's inside it. Got some, alright, that's cool. So we've got data in this array. That's the first good news. Looks like pixel data to me. Cool. So the first one, what was it loading that into? Into surface. We'll just check the surface array in global space. There it is. And that looks like it is full. Yep, surface. So that's getting our data. That's cool. We run through the second time. And that should mean that that looks pretty good. Yeah, that's good. This is our bump mapper image we've loaded into this bump array, and it should be in the global array up here. Yeah, that's cool. Maybe we flipped past that too quickly before. I hope we'll look at the right thing. Alrighty, that seems to be functioning at least, so we'll get rid of the break. We don't want to stop there all the time. We'll just assume that thing works. So what does the rest of this subroutine do? Maybe we should have paid more attention to what this was doing when we were just chunking this together. Put a bit of a billboard around that label so I can sort of see as we scroll through. So we'll do something crazy, and we'll just I won't delete that. Hang on. See how it grabs screen width and screen height? Yeah, there it is. And then it uses that down here. So we've actually cut that out. Or removed that. So whatever it was doing whatever this does, creates the directional normals from the bump map. That's why that wasn't working. And that, oh God. Don't know, let's just try it. I don't think it's actually rendering, calling the render loop. Up here it's got it doesn't render anything unless this is valid. Let's just make that valid all the time. See if we're getting something. We're getting something, but we're not making much sense of it, are we? Right, so what's it? Let's go back to this subroutine. So it's built our normal maps. We better check this stuff actually. We'll put a break in there and we'll just we'll check that we should have in bump here. Yeah, now at least it's got data in it now. It's been populated, so that's cool. That's what we want to see. What about the next bit? So it just uses that bump array temporarily and then just throws it away. Light. So we're initializing the light position, scaling it, dividing by that, dot product. Is this initialized anywhere else? What is this? So we're using the Z form of that. Why are we doing that? Is that in the program at all? There's hardly any. This weird array down here. Where is this thing? It was called constant originally, and it's a set size. But I don't think it was in use. Just saying. No, don't do that. Search. The first time it's used is there. So why is it used? Right. I think we ditch that. We don't need that, surely. I'll just check what type that is. I'm pretty sure it's a float if it's so it's vector 4, was it vector 3? Vector 4 constant, and that was declared as a float. So we'll just have a Z variable there, which is all it appears to be. We might tag explicit on. True, turn me on, and then turn me off. Because I don't really want it. This code wasn't written with that mode. So we'll just go local, this is Z here, if Z is lower than that, alright, then Z equals 0, okie dokie. Integer of Z times this. Fair enough, sounds right to me. Do a bit of a save. Got a dot product, we're inverting it, checking it's under there. Converting it to a, now that needs to be local there as well actually. Alright, what are we getting? Not much. Not much, are we? But let's just check this environment array. I want to see if this has actually got something in it. That would be my first port of call. Stop, thanks. Stop. So that was an array call environment. There it is there. And that looks pretty, oh no. That's good. So we have some data in this array, so we're not our structures are being, our arrays are being filled and created. That's all we need to know initially. So our problem's probably got something more to do with the effect itself, or the rendering itself. Let's just try and splodge some stuff on screen and see if the output is working, because we did change that behavior before. I butchered it, to be honest. That's how our effect there. And this part here, so we've got source row address, copy from source row, source buffer address, okay, and that's source row address, X, Y, source buffer address, screen width times 4 multiplied by that. Now, are these actually accurate? We might read a null pixel in here as well, just to make sure. Whenever you lock a surface, it's possible for you're kind of overriding how the rendering engine works, and you can kind of get situations where it's not focusing on the right thing. If that makes any sense. Well, that shouldn't be any worry here, at least. Just want to make sure it's getting the pointer to here. Screen pointer and screen pitch. They make sense. Seem to be. We'll go up there. We'll put a bit of a poke. We'll poke int destination row address. And we'll add 100 to it, or we'll just add y to it actually. Add y to it, times 4. Ooh, we might crash if we do that. We'll just add 100 to it. And we'll make this a yellow color. So we should be poking into screen memory directly. Hey, well, that fixed it. There you go, it actually works. Yeah, I think that lock buffer, I'm not quite sure. Obviously when you grab the screen pointer here, it must need that to be seated once before. I'll just check if I comment that out. Oh, program's halted. Run it. Yeah, it doesn't like it. It's interesting. Just PB being fussy, I guess. That's all right. So this poke's not needed, and we have a working version of the program. Don't know if it's, well, I think it's the same. It's performing pretty well. We're capturing the screen while we run as well, so we're getting somewhere in the middle there, about 60 frames per second from an interpreter. Not bad, I would have thought. I think we can glean a bit more performance out of those inner loops. I might just chop that out. Since we're comfortable now, we'll just cut that out. I'll probably regret that in a minute's time. Go, ooh, what was the rest of that code doing? Do we need that as a separate thing? We could probably just do the fill memory and fill the entire buffer of this screen, the source buffer here, in one loop, and that might, in terms of the CPU, it's more efficient to do that, because here we're reading a scan line from it, because the destination scan line is going to be of an unknown width. And we're just assuming the back buffer is 32-bit. I mean, there's a whole bunch of assumptions that are going on here. So if we ran this thing in 16-bit full screen mode, it would fail. It wouldn't work at all. But for the sake of the demonstration, it's okay. What we should be able to do here is, well, at the end of the whole thing, if we we fill in this source memory, which is going to be this buffer here, or this address. So we want to fill this thing in with all that good stuff, and we want it to be screen width by screen height. All right, just picking up after another interruption. I think when we left off, we were talking about the rendering loop that draws our effect onto the screen. It was copying a scan line and then it was clearing a scan line as it went. So I've just popped that out of the clearing aspect. I've popped it out of the vertical loop, and we're just doing fill memory of that whole buffer. And performance-wise, it's running a bit better. We're capturing the screen again, so I'm going to have a bit of... the effect looks pretty good. I think it's working the same. I don't see any glaring differences between them. But we are just running on the PlayBASIC interpreter. This is 1.65, by the way. It's a bit stronger than... Well, it's certainly a lot stronger than the free versions. So, what else could we do? There's probably a lot of things we could do to this, but this thing here seems like it's a not great solution. Okay, so we're masking this off. We're keeping the high bits, and that equals 0. Guess it's wrapping it around, I guess. So most of this is just, we're grabbing a pixel, pulling the pixel to pieces, checking for an overflow, and we only need to check for an overflow. Well, actually, sorry, going back here, it is checking if the alpha is being used or not. But what we could do is we could have two versions of this inner loop. We might be making it right for our own back though, really. We could probably simplify some of this inner loop here by using a pointer, a typed pointer with a static array in it. And that would give us the same behavior, but we could just step across in integers. How's this loop rendering? Yeah, so we're rendering in, we're moving in pixels, but here we've got these pixels computed out to be the raw addresses, and we're plotting across. Yeah, is it worth doing that? It probably would be. You'd probably get a nice gain. Like what I'm talking about here is that if we know there's alpha, and we know alpha, in fact, if we just check the environment value here, probably a better way of doing this is if we know that this level here is never higher than 255, then these clips are never needed. It's impossible for it to actually overflow. So we'll do a bit of a quick check, and we'll look at the that particular array. Oh, hang on. Yeah, so it's running. Go here. Now, back buffer is our buffer, and we want the environment array. Let's have a look. Up to 100 by the looks of things there. 1, 2, yeah. So if we read a level from there at 0, we just don't do anything. So the output color is black. So this clipping is not needed. We'll just assume that anyway. I think that's the case. Bit of a quick save and see how we go. Oh no, I've got some overflows there, so we do need that to not overflow. And just judging by the amount of pixels in there, we can definitely swap the two things around, I think. What I mean is we check if the alpha level is at least 0 or above 0, it's not 0. Then we could go, if alpha is below 256, it does this version of that. In fact, we just needed to do that here. So we're reading the pixel, checking to see if it's below that. If it is, we'll just go here and we'll go, is it above 255? If it is, then we'll apply our clipping. The if-thens there actually are probably unnecessary as well, come to think of it. End if. We'll just see if that corrects our little mistake. I better check where that's the buffer we were reading from before. It probably isn't. So, yeah, the environment buffer there. Alright, so the second pixel is rendered the way it was, and the previous one is selecting if it's going to clip the RGBs or not. Because I don't think I know that the RGB command doesn't have this clipping built into it. It probably should have, actually, to be in all honesty. That's a bit surprising. Okay, welcome back. I had yet another disturbance. It's about the third or fourth time I had to try and get this thing done. I'll have a quick run of the application to refresh ourselves, refresh myself. It's our bump mapping demo ported from Dbpro. What we might do is we might try and add some optimizations, clean the code up a little bit, make it a bit more PB friendly, I guess, or more PB rather than anything else. And the first port of call, we'll go through some of these bits and pieces, some of these loops. I understand why it was, I think in the original demo, it was using an array to store these things, and an array access, a two-dimensional array access, is quite expensive. But there are things in this loop here that we can do to make this even a bit easier, actually. Since we've got two loops, we've got an outer loop and an inner loop. I did notice that there were some pixel problems before too. I'll just restore this to what it was before. So we're grabbing our light level, grabbing our pixel, splitting the components, the RGs and G and B apart, multiplying them out, and there we go. and recombining them. Now just check the other one's the same, just to restore it back to how it was, or how I remember it being anyway. Looks pretty good. That'll do us. So there's some of these kind of inner loop logics look a bit off to me. I guess we're trying to make sense of code that was already optimized, which in itself is a bit of a problem. Those optimizations would have suited the other language. They're not necessarily, that really makes sense in this particular situation. But you know, we'll put up with it. We could, I think we could change this structure here and actually have a structure and then replace. We probably get rid of at least 2 instructions per pixel, which doesn't sound like much, and then maybe a few more there actually. A few more instructions there as well. Same as this thing here. So it's got a clip and it's checking to see if there's an underflow by doing a mask. So if this integer here was negative, these high bits here would be set. We probably could just mask those out and have it wrap the pixel around. I'm pretty sure the texture is actually a power of 2 in width. So we might get some artifacts from doing that, but you mightn't notice the artifacts really. Now this is our copy routine for copying the data to the screen. We really don't need this, to be honest. We could have an effect surface and get the pointer to the effect surface and just copy this data straight across to it, and just use CLS really. Do I want to do that? I don't know. All the code at the bottom is just setup code. We can get rid of those things there. They don't need to be there. That was our original subroutines. I'm not sure why this is not a function actually. It would have made sense to me for that to be a function. I've got the explicit mode enabled there. I think I was tracking down some variable usage. Okay, so in Dbpro you can't actually pass arrays. In PB you can pass them. So I could pass these as arrays into here, but I could just use the stock images as well. As in, if I load this into what's called an effect surface, which is a version of the image that's stored in system memory, not in video memory, the cost of reading pixels from that is quite low. It's basically the same as just, in fact they are really just the same as allocating a bank and peeking and poking from it. So in this case I could probably reduce the complexity by going back to something like that. There's a lot of legacy sort of material in here. So this is the address of the source buffer address. Some of the arrays don't need to be there, I guess. Not doing a very good job optimizing it so far, are we? Or just trying to make it a bit cleaner than what it really is. I don't believe that vector array there is in use anymore, so that can be eliminated, and it's not. So it's just redundant code, and vector 4 I think was redundant as well. We'll just rename it and see if it complains. No, so it's not in use. Don't need those things there. Don't really need these things here either. Environment. Okay. surface back buffer. Are we using back buffer at all? I don't remember any references to back buffer as an array. I'll have a bit of a quick look, see if they are. That's the dimension statement, and there's nothing else in it. So let's get rid of that. Comment it out, quick save, bit of a run, and nothing there. Those things won't affect the performance. This week we've got clutter upon clutter. We don't need it. These could all just be banks instead of being arrays to begin with. Given that it's hard-coded to be 256 pixels square. Anyway, we'll go back to this inner loop here, or these inner loops here. These are the ones that make the difference, really. The rest is just posturing, cleaning up a bit of code. It's not that useful, really. What I was thinking we could probably do, we've got bump map row address, and it's storing 2 pixel offsets, 2 coordinates. We're adding the light to it. Now, does line ever become negative? I don't know. So this is the actual blending routine. I was thinking before that what you could do is that you could take this alpha level, which is clearly just an 8-bit number, and we're multiplying that by each separate RGB field. What we could do is we could use I think it's the RGB alpha mult function. If we converted this to a 24-bit color, we could just take the pixel here, do a multiply of it, and then write it back to memory. But looking at this now, it's actually doing something a bit interesting. Notice how when it grabs the R channel from the color, it's doubling this at the end. So I think if we use that approach, we'd affect the brightness. We'll give it a go. Just comment that stuff out, man. We're going to have to change the what's stored in this other array as well. But what I'm thinking is we could just go something like this. We're reading from that location and we're poking to here. And we're going RGB alpha mult. And it will be pixel multiplied by the alpha level. At the moment, that would just keep the blue component because the red and the green are not actually the same value. Just do a quick. So see how we've got a blue tinge? That's kind of neat. Alright, so we'll do the same thing for the other, because this inner loop is drawing 2 pixels at a time. It's obviously more efficient to do it like that, to get rid of some 4 next loop overhead. In some basics, 4 next loops can be quite, they can chew up a lot of time. Alright, so the whole thing should have a blue tinge to it now, and it does. But our performance is up to 100 frames per second. Now, I think we'll say about 90 on average. That's pretty cool. What we need to do though is this environment array, because the other operation, what it's doing here is when it grabs red, for example, it's pulling this down, pulling the red bits, which are that sort of bits 17, 18 up to 24, pulling them down by 16. It moves them into the bottom byte, does the multiplication, and then it rather than shifting it all the way back, it lets it be a little bit over. So maybe when we create the environment array down here somewhere, there it is. Let's just multiply that by 2. We're changing the effect a little bit, I guess, but I think for the most part, we'll get pretty much the same result. To get rid of the blue, we need to make this into a color. So the red, green, and blue channels are the same value. And that should bring us back to where we were. Possibly a bit brighter now, isn't it? That works because we're replacing some interpreted logic with just one function that does that same or much the same logic for us. The RGB mult or alpha mult command is useful for doing like depth queuing. So that's why it's in PB. Cool, pretty cool. We'll have a bit of a go at this other inner loop. I think we've changed the aesthetic of it a little bit there, but you know, that's all right. We can do that. We could probably just use clip X there, because here we're just concerned if the source X is within that constraint. We have to do the clipping before we read from here, otherwise it'll be upset. That's okay. At no point are we even looking at what these values are. We probably should have a look at what they actually are. If we find out that y is constant for the whole row, that we don't need to calculate every pixel, because the light's not moving inside the loop. Yeah, it's a bit of a mess, this program. I mean, it works. It's a good example of, you know, the original was faster than my optimized version was faster than the other one, but it was not really intended to be used in any real world situation. I think what we'll do is we'll make a typed pointer that we initialize at the start of the row that we're reading these bump XY values out of, and that will have a pair of these XYs, and then we'll move that along, and that should save us at least 3 additions per pair of pixels. It should. I don't know. So up here we'll have a little structure. What we call it? Type. What does it call itself? That's bump normals. Type bump. Well, it uses pixel offsets, so we'll call it pixel offsets. Pixel offsets. And type, thank you. So we've got x1 and the y1 coordinate, x2 and y2. Let's go back to where we were, roughly. Right, so here, dim row as this pointer. Now I've got to assign this other thing bump. I will use that same thing for the time being, and then we'll cull it out just in case something else uses that. I don't want it crashing straight away. So, and now our pointer is pointing at the first group of pixels, and we should be able to get rid of this pair at least. So source X is going to equal row x1 plus light x, and source Y is row y1 plus y2. Just place those down there. Now we'll have to increment those as we go across, as we draw these pairs of pixels, but we'll do that in a second. Now this is the next pixel, and the next pair of reads. Again, I don't remember why it's stored like that, but that's just the way it is. So we'll optimize what we see and not worry about what we don't. So on the end here, we've got to move row equals row. I've got to int that actually. Int plus size of, and we want our type. What was the name of the type again? Bump pixels offsets. Yeah, we'll call it bump pixel offsets. Getting fussy in my old age, you know. Where are we up to here? So this, what size Oz does, works out the number of bytes this structure actually takes up. So we're moving the row pointer along in that space. I think our definition is wrong up here. I think I've used pixels, yeah. Nope. Pixel offsets pointer. Let's give it a test run. We've got a few frames one back by just using a structure that PB is more comfortable with. I think we'll clear that code out. From there, we've got this clipping thing in here too. Obviously, if we could get rid of the clipping, we would get a better result. Sometimes what can happen actually is doing this comparison here might cost us more than doing the blend. It would depend on how frequently this environment value here is 0. If it's very frequently 0, then we're saving ourselves time. If it's not very frequently 0, we're actually costing ourselves time. Just something to be a bit conscious of. This is the unrolled code again. So this loop draws a pair of pixels every time it steps through. And this equates really just to this integer addition. It's no different than what this does, but when you have a pointer and you do arithmetic on it, they function a little bit differently. Just letting you know. All right, we'll give this a bit of a look. Actually, I don't know what these values are. Like, we might not need these values at all. Because if those rows, if they're just always the same all the way across the row, then why are we reading them? That's crazy. I don't know. You tell me, we'll find out. So what I'll do is I'll just put a print across the row, and we will just break all up here. I'll put a bit of a print at the start of the row. Something useful, like a bunch of those. And then at the end of this loop, we'll break. Right in debug mode. So on the console, yep. Okay. They do vary, so it's getting caught up dumping stuff to the console. Yeah, program halted. You can see there we're getting some pretty wild values coming through it, so we do need to clip them, and we can't just optimize that out of the loop. Or quite obviously, I can think of one way you could optimize that table out, but it would cost a lot of memory, and for the purpose of the video, it's not really worth doing. You could, if you know that the light values are the positions or the possible limits of where that light can be, you could pre-calculate the tables. Didn't say it was a good idea, but you can do that. So it costs you a bunch of memory in this case, though. Let's have a look at what that table it's doing. Why is it making this table to begin with? Right, so this is our image, and it's making our bump map table, which is really just a grayscale version, normalized. It does this up here somewhere. That's it there, I would say. No, it's not it. This version here is just copying the data into these arrays and streamlining it, so we've got the X versions of the normals and the Y's together. Which is okay, it's fine. Should pay more attention to what it's doing, really. Back down the bottom. There it is. That's the bit of code. Alright, so normal X is really taking the difference of the pixel. So the current coordinate is really the difference between the coordinate on the right hand side and the left hand side of it. Minus X. Why are we subtracting that from it? Why are we doing that? Just seems unnecessary to me. There's probably a good reason for doing it. Obviously, it's set up to run that way. But we might be ruining ourselves later on. We might be doing a bit of extra pre-processing here, feeling good about ourselves, but it might make the at the runtime loop in here more complicated than what it need be. Just saying, you know. I think what we'll do for these comparisons, we'll just mask them out. How bad can it be? We'll see what it does anyway. We'll see if it's upset by that. Source X equals source X and the bottom bit here. We're going to get reads that are outside the boundaries here that will rotate weird. But for the effect, it might not matter. I don't think it really makes that much difference. Once we're in the middle of the playfield and we're not wrapping around the edge of the playfield, then we shouldn't really be paying any penalties for it. Oh, there we go. We're getting some artifacting there. See that pixels over here before? That's why we always check when we make changes to things to try and clean them up without understanding them. It's always good to check it to make sure, well, does that work or are we making it worse? I think we're probably making that worse. We'll revert back to where we were. That's all fine. I'm okay with that. That's fine. The source pixels here, we could probably have, do we need source and destination? Do we even need that to be on a destination playfield? Like we could get away with writing to an effects surface, and that would be just as convenient. It would be more convenient than what we've got here. Anyway, I think for what we've got it to perform pretty well, even though I'm capturing the screen as well. So 100 frames per second, 90 frames per second, pretty happy with that. On, in PB, which is an interpreted language, it is what it is. I think we could definitely get better performance by just fishing around a little bit more and understanding why some of these data structures are set up the way they are. Which I think it's kind of obvious that that's probably the limit here. But that's okay. That's okay. Anyway, I hope this was remotely useful. I hope this hasn't been a massive waste of time. It's taken a long time to produce this video for two people to watch it, But that's cool. Enjoy yourself. Stay safe and have fun coding and hope the world is going well for you. Bye. See you later.